What's up guys, my name is Ritvik and today I'm here to teach you everything that you need to know about AP Calculus BC Unit 10. And before I begin, don't forget to go to the description to get my free AP Calculus BC book because that book has basically everything that you need to know to get a 5 and an A in your class. So now let's begin. So let's define convergent and divergent infinite series. So a divergent series is one that has a sum that is infinite or does not exist. On the other hand, a convergent series has a sum that exists and is finite. Now for any infinite series, the partial nth sum is noted as S of n, and it's a of 1 plus a of 2 plus all the way to a of n, so the first n terms. So now let's look at geometric series. So basically there's a ratio r, right? And we keep on multiplying each previous number by this ratio r. And an infinite geometric series will converge when the ratio, right, the absolute value of the ratio is less than 1. And it will diverge if the absolute value of the ratio is greater than or equal to 1. And then if the geometric series converges, then we can find the sum by using the first term and dividing that by 1 minus r, where r is the ratio. Now the nth term test for divergence. Now if the limit, right, of a of n as n approaches infinity, if that's 0, then that means the series for a of n will diverge. However, if the limit of a of n, right, as n approaches infinity, if that approaches 0, then the result is inconclusive. And that means you must use a different test. Now let's look at an example. So the series 3 to the power of n divided by 7 to the power of n plus 2. Does this series converge or diverge? Well, let's write 7 to the power of n plus 2 as 7 to the power of n times 7 squared. And then we can bring the 1 over 7 squared out to get 1 over 49 times the series of 3 over 7 to the power of n. And we notice that each term has a ratio of 3 over 7 for this infinite geometric series. So clearly it converges because that ratio is less than 1, and we can find the sum of the infinite geometric series by using the first term divided by 1 minus r, where r is the ratio. So the first term is 3 over 7, and the ratio is also 3 over 7. So we can find that the sum of the geometric series is 3 divided by 4, and then we multiply this to 1 over 49 to get 3 over 196. Now the integral test. Now this is a useful test, and it's used for both convergence and divergence. Now the integral test has some conditions. Our function f must be positive, decreasing, and continuous for a certain interval, right, from k to infinity. And if that occurs, then the series for a of n and the integral, right, they can both either converge or diverge together. And this is useful because if we're given a series and we want to figure out whether it converges or diverges, then we can use the integral test. And after integrating, right, if our integral converges, then that means the series must also converge. And if the integral diverges, then the series must also diverge. And for the integral test, you must know improper integrals really well. And the reason is that our integral has bounds of infinity. Now the harmonic series and p series. So p series is in the form 1 over n to the power of p, where n goes from 1 to infinity. And the p series converges if p, right, that exponent, if it's greater than 1. And it will diverge if p, that exponent, if it's less than or equal to 1. And an important tip to using the p series test is to convert all the radicals to exponential form. On top of that, if you have a negative exponent, such as x to the power of minus 2, right, then you should write that term as 1 over x squared. So let's use the integral test on 1 over n times the natural log of n. So let's integrate 1 over x times the natural log of x from 4 to infinity. So we now bring in a limit, and we make the limit approach infinity, so we can integrate by using u substitution. So we substitute u equals to the natural log of x, and then we can differentiate the substitution to get du equals to 1 over x, since the derivative of the natural log function is 1 over x times dx. And now we substitute both of these things in to get the limit as n approaches infinity of 1 over u du. However, there's one problem. The integration bounds that we had before from 4 to n cannot be used anymore. And the reason is that we did u substitution. And whenever we're doing u substitution for a definite integral, we should change the integration bounds. And to do that, we simply substitute 4 and n into u equals to the natural log of x to find the new integration bounds. And doing so gives us that the lower integration bound is the natural log of 4 and the upper integration bound is the natural log of n. And then we can integrate 1 over u to get the natural log of u. And after using our bounds, we get the limit as n approaches infinity of the natural log of the natural log of n minus the natural log of the natural log of 4. And we can notice that as n is approaching a super high value, right, then the natural log of the natural log of n will also be approaching infinity. This means that the integral diverges, and since the integral diverges, the series must also diverge by the integral test. Now let's look at the comparison test. Now if u is less than a of n, which is less than or equal to b of n for all values of n, then the following two things must apply. First, if the series for B of n converges, then the series for A of n must also converge. And then if the series for A of n, if that diverges, then the series for B of n must also diverge. And please only compare a series with a known series. And if you want to see examples of this, you can check out my free book linked in the description below. So let's look at an example of the comparison test. So does the series 1 over 6 to the power of n plus 5 converge or diverge? Well, if we want to use the comparison test, we need to find a series to compare this to. Well, in such situations, right, you remove the constant terms such as 5, and then we can compare to 1 over 6 to the power of n. And 1 over 6 to the power of n plus 5 is less than 1 over 6 to the power of n for all values of n. And we can notice that the series for 1 over 6 to the power of n must converge. And the reason is that we use the geometric series test. So the ratio between each term is 1 over 6, and that's indeed less than 1, so that converges. And since 1 over 6 to the power of n converges, then that means the series for 1 over 6 to the power of n plus 5 must also converge by the comparison test. Now let's learn about the limit comparison test. So if A of n is greater than 0 and B of n is greater than 0 for all values of n, and the limit as n approaches infinity of A of n over B of n, if that approaches a value L, where L is a positive finite constant, then the following relation below applies. The series for A of n and B of n can either both converge or diverge. So this is useful because if we compare it to a known series, now let's look at an example of this. So does this series, a to the power of n plus 2 divided by 3 to the power of n minus 4, does this converge? Well, let's use the limit comparison test. So again, remove the constant terms to find a series to compare it to. So we removed positive 2 and we remove negative 4, and we're left with a to the power of n and 3 over 3 to the power of n, and that's B of n. And we can notice that this series, right, for B of n, it must diverge because the ratio between each term is 8 over 3, which is greater than 1, so it diverges by the geometric series test. And now we can find the limit as n approaches infinity of A of n over B of n. And we can notice that it's clearly approaching 1, which is a positive finite constant. And since B of n, the series for that diverges, then that means the series for A of n, which is a to the power of n plus 2, divided by 3 to the power of n minus 4, must also diverge by the limit comparison test. Now let's learn about the alternating series tests. So basically these two series, where n is going from 1 to infinity of negative 1 to the power of n times A of n, or negative 1 to the power of n plus 1 times A of n, they will both converge if the following two conditions below are true. The first one, the limit as n approaches infinity of A of n, if that's 0. And then the second one is that A of n plus 1 must be less than A of n for all n. And this means that A of n, right, that term must be decreasing as n is going up, and it must be approaching 0. And if that is true, then we can use the alternating series test. Now the ratio test. Now the ratio test says that the series of A of n converges when the limit as n approaches infinity of A of n plus 1 divided by A of n, the absolute value of that, if it's less than 1. And that same series will diverge if the absolute value of A of n plus 1 divided by A of n is greater than 1. And remember that if our limit now is 1 instead, then the ratio test is inconclusive and another test must be used. And this works really well with stuff like factorials and exponents, and the reason is that so many things cancel out. For example, if A of n is something involving n factorial, then that means A of n plus 1 will be something with n plus 1 factorial. So if we divide both, we can see that so much cancels out because n plus 1 factorial is the same thing as n plus 1 times n factorial. Now let's look at an example. Does this series, e to the power of n divided by n factorial, converge or diverge? Well, we know that A of n is e to the power of n divided by n factorial. So let's find A of n plus 1. So we substitute n plus 1 for n, and we get e to the power of n plus 1 divided by n plus 1 factorial. Now we can find the limit as n approaches infinity of A of n plus 1 divided by A of n. So we can see that most of the things cancel out. After canceling everything out, we're left with the limit as n approaches infinity of e divided by n plus 1. And as n is approaching a super high value, e divided by n plus 1 will be approaching 0. Now determining absolute or conditional convergence. The series of A of n will converge absolutely if the series for the absolute value of A of n converges. And then the series for A of n will converge conditionally if the series for the absolute value of A of n diverges, but the series for A of n converges. On the other hand, the series for A of n will be called divergent if both the series for A of n and the absolute value of A of n diverge. And this topic is more focused on terminology, so I highly recommend memorizing these three terms that are bolded. Now the alternating series error bound. Now if S of n represents the nth partial sum of a convergent alternating series, then the error bound will be bounded by the first term that is not included in the partial sum approximation. So basically, S of n represents the approximation for a certain series. And then S of infinity that you see is basically the sum of all terms. So that's the actual sum. So the difference between these two, right, will be bounded by the n plus 1th term, which is the first term not included in the nth partial sum. So let's look at an example. What is the error bound for the third partial sum of this series, negative 1 to the power of n times the square root of n divided by 4n plus 1? So, since we want to find the error bound for the third partial sum, that means the error bound, right, it will be bounded by the fourth term of the series. So we substitute 4 into the square root of n divided by 4n plus 1. And after substituting that in, we get 2 over 17, and that's the error bound. Now, let's find Taylor approximation polynomials for functions. If we have a differentiable function f of x, then our nth degree Taylor polynomial for the function f centered at x equals to c can be found using the expression below. Please pause the video and carefully look at and find patterns to remember this form. And in general, the coefficient of the nth degree term for the Taylor polynomial that is centered at x equals to c will be c plugged into the nth derivative divided by n factorial. Now the Maclaurin polynomial is a special type of a Taylor polynomial. Basically, it's just a Taylor polynomial, however the center c is 0. So to find the Maclaurin polynomial, you simply plug in c equals to 0 into the Taylor polynomial. Now let's find the second degree Taylor polynomial for the natural log of x centered at x equals to 2. So, using the form that I just showed you for a Taylor polynomial, we can get that the second degree Taylor polynomial will be f of 2 plus f prime of 2 times x minus 2 plus f double prime of 2 times x minus 2 squared divided by 2 factorial. Now since f of x is the natural log function, we can find that f of 2 is the natural log of 2. And then since f of x is the natural log of x, then f prime of x, right, the derivative of that will be 1 over x. And we can plug in 2 to get f prime of 2 is 1 over 2. And then the second derivative of this function will simply be negative 1 over x squared. And we plug in 2 to get that f double prime of 2 is negative 1 over 4. And then we can plug all of this into our Taylor polynomial to get that the second degree Taylor polynomial is the natural log of 2 plus 1 half times x minus 2 minus 1 over 4 times x minus 2 squared divided by 2 factorial. Now let's learn about the Lagrange error bound. Now basically the Lagrange error bound is between the actual function and then the nth degree polynomial, basically the one we use for approximation. So f of x represents our actual function, while p of n of x, that represents the nth degree polynomial. And then the error bound will be the maximum value of the n plus 1 derivative times x minus c to the power of n plus 1 divided by n plus 1 factorial. So the tricky part here is that we want to find the maximum value of the n plus 1 derivative. So usually you'll be given that value in a problem, or you'll be given a graph and you look for that maximum value. So it just depends on the problem itself. Now the radius and interval of convergence of a power series. Now you can see how a power series is represented on the screen. And then a power series is basically centered at a value such as x equals to cu. Now to figure out how a power series converges, you must use the ratio test. So basically you find the limit as n approaches infinity of a of n plus 1 divided by a of n, which is what we used in the ratio test also. So basically if that limit equals to 0, then the series converges for all values of x. So from negative infinity to infinity. Now if that same limit is less than 1, then the series converges to an interval. And if that same series, if it approaches infinity, then the series converges only to the center at x equals to c. Now if that limit of a of n plus 1 over a of n, if that's less than 1, then I already said that the series will converge for an interval. So that's when we need to find an interval of convergence. And whenever you're finding the interval, right, you must check the endpoints. So you plug in each endpoint, right, into the series for a of n. And if that series converges, then you include that endpoint into your interval of convergence. However, if the series converges at an endpoint, then you don't include that endpoint into the interval of convergence. Now finding Taylor or Maclaurin series. Now it's very important to know how a Maclaurin series is represented for some of our common functions, such as e to the x, sine of x, cosine of x, and 1 over 1 minus x. So please pause the video and look at these representations. Now if you want to see the general notation for each of these Maclaurin series, check it out in my book. It's all in there. Now, using what I just showed you, you're going to be representing functions as power series. So basically, you're going to be using these common functions to write actual representations. For example, if you want to write the Maclaurin series for sine of 2x, So all you do is you use the general Maclaurin series for sine of x and you simply plug in 2x into it. So this is all about manipulating our common power series to find the desired power series. Now let's look at an example from the actual AP exam. So please pause the video and carefully read this problem and try it. Now by now I hope that you actually paused the video to try the problem. So let's look at the solution. So basically we're given that the Maclaurin series for the natural log of 1 over 1 minus x is x to the n over n. And this has an interval of convergence from -1 to 1. And it's not inclusive of 1. Now we want to find the Maclaurin series for the natural log of 1 over 1 plus 3x and determine the interval of convergence. Well, we can notice that we can use the given Maclaurin series. So we're given the Maclaurin series for the natural log of 1 over 1 minus x. So if we plug in -3x, 4x into this, then we get the natural log of 1 over 1 plus 3x, which is what we want. So we simply plug in -3x into the Maclaurin series for the natural log of 1 over 1 minus x to get -3x to the power of n divided by n. So we know that a of n is -3x to the power of n divided by n. And then a of n plus 1 is -3x to the power of n plus 1 divided by n plus 1. And now using this, we'll find the limit as n approaches infinity of a of n plus 1 over a of n, because this will allow us to find the interval of convergence. Now using this limit, right, we'll make it be less than 1, since we know that something will only converge to an interval, as I just said, when it's less than 1. So we want this limit to be less than 1. So if I can evaluate the limit to get the absolute value of 3x, and that's less than 1, which means -1 over 3 is less than x, which is less than 1 over 3. And now our endpoints are -1 over 3 and 1 over 3. So let's substitute -1 over 3 into our Maclaurin series for the natural log of 1 over 1 plus 3x. And doing so gives us 1 to the power of n over n. And we should notice that this is a harmonic series, which is a special type of a power series. And this must diverge. Now we plug in x equals to 1 over 3 to get -1 to the power of n divided by n. And this must converge due to the alternating series test, since the value of 1 over n, right, it's decreasing and it's approaching 0 as n is increasing. So it must converge due to the alternating series test. And this means that we do not include -1 over 3 into our interval of convergence. And so our final interval of convergence is from -1 over 3 to 1 over 3, and it's inclusive of 1 over 3, not -1 over 3. Now in part B, we want to find the summation, right, from 1 to infinity of -1 to the power of n divided by n. Now to do this, we know that the Maclaurin series for the natural log of 1 over 1 minus x is simply x to the power of n divided by n. Now we simply plug in x equals to -1 into this, because doing so gives us a Maclaurin series of -1 to the power of n divided by n, which is basically what we wanted to find. So doing so gives us the natural log of 1 over 2, which is the sum of the desired series. Now in part C, we want to give a value of p such that this series, -1 to the power of n divided by n to the power of p converges, but the series for 1 over n to the power of 2p diverges. Now, the series 1 over n to the power of 2p will diverge when that exponent, which is 2p, will be less than or equal to 1. And this is by the p series test, which means that p must be less than or equal to 1 over 2. So the series -1 to the power of n divided by n to the power of p. So we can use the alternating series test to get that this series will be converging, right, when 1 over n to the power of p is decreasing in value and approaching 0. And this will occur when p is greater than 0. So we can choose any value between 0 and 1 over 2, such as p equals to 1 over 2, and then both conditions that were given in the problem will be satisfied. Now let's look at part D. And in part D, we want to do the similar thing again. We want to find the value p, right, such that the series 1 over n to the power of p diverges, but the series 1 over n to the power of 2p converges. And we want to give reasons why our value p is correct. So we simply use p series on both tests. So the series 1 over n to the power of p will diverge when p is less than or equal to 1 by the p series test. And then the series 1 over n to the power of 2p will converge when that exponent 2p is greater than 1, which means that p must be greater than 1 over 2 and it must be less than or equal to 1. Now let's look at another free response question from the actual AP exam, so please pause the video and try the problem on your own before you proceed with the solution. So by now I hope that you actually paused the video to try the problem, so let's look at the solution. So basically in this problem, we have a function f that's defined by 1 over 1 plus x cubed, and then the Maclaurin series for this function is given as 1 minus x cubed plus x to the power of 6 minus x to the power of 9, and so on. And we're given that this converges from -1 to 1. Now we want to find the first three non-zero terms and the general term for the Maclaurin series for f prime of x. So The general term of this Maclaurin series can be found by differentiating the general term of the Maclaurin series for the function f. So we're given that the general term for the Maclaurin series of f is negative 1 to the power of n times x to the power of 3n. And we can differentiate that to get negative 1 to the power of n times 3n times x to the power of 3n minus 1. And now to find the first three terms for the Maclaurin series for f prime of x, we simply differentiate some of the terms of the Maclaurin series for f of x. So we can differentiate 1 and we simply get 0. We differentiate negative x cubed, we get negative 3x squared. We differentiate x to the power of 6 and we get 6x to the power of 5. And now we differentiate minus x to the power of 9 to get minus 9x to the power of 8. So that's the first three terms. And in part B, we wanted to use the results from part A to find the sum of this infinite series. And the general term for this infinite series is negative 1 to the power of n times 3 to the power of n divided by 2 to the power of 3n minus 1. So we already know that the general term for f prime of x, right? The series for that is negative 1 to the power of n times 3n times x to the power of 3n minus 1. So we can plug in x equals to 1 over 2. And the reason is that if we plug in 1 over 2, we get the desired series that we're given for part B. So plugging in x equals to 1 over 2 gives us that the sum of that series is f prime of 1 over 2. So to find that, we can differentiate f of x to get f prime of x is minus 3x squared divided by 1 plus x cubed squared. And we plug in 1 over 2 to get that f prime of 1 over 2 is negative 16 over 27. Now in part C, we want to find the first four non-zero terms and the general term for the Maclaurin series representing the integral of this function f from 0 to x. So again, we manipulate the given Maclaurin series that were given initially in this problem. So we integrate the general term for the function f, right? And if we integrate that, we get that the general term for the integral of this function f will be negative 1 to the power of n times x to the power of 3n plus 1 divided by 3n plus 1. And now using this general term that we just found, we can find the first four terms by simply plugging in terms such as n equals to 1, n equals to 2, and we can find the first four terms. Now in part D, we want to use the first three non-zero terms of the infinite series that we found in part C to approximate the integral of f from 0 to 1 over 2. And then what are the properties of the terms of the series, right, representing the function f from 0 to 1 over 2, the integral of that guarantees that this approximation is within 1 over 10,000 of the exact value of the integral. Whenever a problem has a word such as within and then we're given a bound, we should immediately think about the error bound. Basically, we can approximate the integral of 1 over 1 plus t cubed, right, from 0 to 1 over 2 by simply using the Maclaurin series. So we simply plug in 1 over 2 into the Maclaurin series that we found for the integral of the function f. So we found that Maclaurin series was x minus x to the power 4 over 4 plus x to the power 7 over 7, etc. So we plug in 1 over 2 into this to find the integral of the function f from 0 to 1 over 2. So we can find an approximation of it, and it's 1 over 2 minus 1 half to the power 4 divided by 4 plus 1 half to the power 7 divided by 7. And then we know that the series in part C alternates and decreases in absolute value towards 0. And that means we can use the alternating series error bound. So the alternating series error bound will be the first term that is not included in the approximation. So the next term is 1 over 2 to the power of 10 divided by 10. And that's the error bound. And we can find that error bound is 1 over 10,240. And that's indeed bounded by 1 over 10,000. And we're done with the problem. Now thank you so much for watching this video. And please don't forget to like, share, and subscribe, since that's going to tell me that you guys are truly enjoying and learning from the books and the videos that I've been making for you guys. And don't forget to join the Discord server to meet other hardworking students that are preparing for various competitions and exams such as the AP exams. And also, don't forget to follow the Instagram if you have Instagram to view educational reels and cool animations. And again, thank you so much for watching this video, and I really hope to see you soon back again on this channel.